What do we think when we see this picture? It is ironic to think that computing systems capable of solving 100 million operations per second are unable to understand the meaning of visual forms or to distinguish between different classes of objects. Sequential computing systems are successful in solving mathematical and scientific operations, in creating and maintaining electronic communication databases, or even controlling appliances so they are more efficient and easier to use. But the difficulty of the computing system lays on their great inability to interpret the world. This system works under the philosophy of sequential systems developed by von Neumann, and this inability has made many researchers focus their attention on creating a new system of information processing, which would allow them to solve everyday problems just as the human brain would do. The human brain has many characteristics which are desirable for any computing system. It is robust and failure tolerant. Many neurons die daily, and its performance is not affected. It is flexible. It adjusts to learning environments without the need of programming it. It can handle fuzzy information, noisy or inconsistent. It is highly parallel, and it's small, compact, and consumes little energy. The human brain is a remarkable computer, capable of interpret and information provided by the senses at an incredibly rapid pace. He managed to discern a whisper in a noisy room, a face in a dimly lit alley, and read between lines in a speech. And what is the most impressive of all is that the brain learns without explicit instructions of any kind to create internal representations that enable these skills. Based on the efficiency of process carried out by the brain and inspired by its performance, several researchers have developed over 30 years ago the theory of the artificial neural network, which emulates the biological neural networks and which have been used to learn problem-solving strategies based on examples of typical behavior patterns. The theory of artificial neural networks is an alternative to classical computing. Those problems where traditional methods have failed to provide convincing results, maybe the artificial neural networks will succeed. So far, the most successful applications of artificial neural networks are image and voice processing, pattern recognition, planning, adaptive interfaces human-machine systems, prediction, control, and application. To understand all this, it's important to know the operation of a biological neuron first. Well, the brain consists of a large number of about 10 to the 11th power of highly interconnected elements named neurons, each neuron with about 10 to the 4th power of connections. These neurons have three principal parts: the dendrites, the cell body, and the axon. The dendrites, which are receptors responsible for loading electrical signals to the cell body. The cell body, who takes the sum of all these input signals, and the axon, a long fiber that carries the signal from the cell body to other neurons. The connection between the axon of a neuron and the dendrite of another is called synapse. The length of the synapse is determined by the complexity of the chemical process that stabilizes the function of the neural network. A simplified diagram of the interconnection of the two biological neurons can be explained using the following model. Let's assume this neuron receives an impulse from another one through this dendrite. It goes through the cell body, right through the axon, arriving to the tail, where it connects with another neuron, creating a synapse. And this other neuron does the same work, receives the impulse, processes, and generates an answer. Research has shown that neural structures continue to change throughout life. These changes include strengthening or weakening synapse connections. For example, it is believed that new memories are formed by modifying the intensity of these synapses. And if you modify them, you create a different response. It is also believed that remembering the face of a new friend is made through the modification of several synapses. So, as well as the modification changes, the answer is different. Researchers, in actuality, want to see these connections in the brain. So is the Human Connectome Project made for. The Human Connectome Project is the first large-scale attempt to collect and share data of the neural connections happening in the brain. When doing this, we will be able to address the fundamental questions about how our brain works and which part interfere when we see, hear, smell, taste, or even talk. Now, let's talk about artificial neural networks. Artificial neural networks don't reach the brain complexity. However, there are two similar aspects between the biological and artificial networks. First, the building blocks of both networks are simple computational elements. However, in artificial neural networks, they are much more simpler. And second, that the connections determine the function of the network. Let's see the characteristics of an artificial neural network. The model of an artificial neuron is made for imitate a biological one, in which the input terminals are the dendrites, the cell body would be the integration zone, and the axon are the output terminals. In this system, we already have three terminals connected. However, they generate no answer. If we add one more impulse, it is processed by the integration zone, generating one answer. If we add another impulse, goes through the same way and generates a second answer. If we add one more impulse, it generates another answer. The difference between an artificial neuron and a biological neuron is that in the artificial, the pulse must be continuous, instead than discrete pulses as in a biological neuron. If we cut a pulse, the whole system fails, which doesn't happen in a biological neuron. Now, let's speak about the perceptron. The perceptron type network was invented by psychologist Frank Rosenblatt in 1957. His intention was to illustrate some fundamental properties of intelligent systems in general. The first model was developed in a biological environment, mimicking the human eye. It was called the photoperceptron. It was a device that responded to optical signals. As shown in the figure, light strikes the sensitive zone, then goes to the association zone, and finally to the response zone. For example, the light impulses generated by a ferret go to be received by the sensitive zone. They are analyzed in the association zone and finally activate a response zone. In this case, the name of the pet, Samantha. The perceptron was initially a learning device, and its original configuration, it was not able to distinguish very complex input patterns. But through a process of learning, it was able to acquire this capability. Through these investigations, it was demonstrated that the perceptron could correctly classify patterns in what Rosenblatt called a differentiated environment, in which each class was made by similar patterns. The perceptron was also able to respond consistently while dealing with random patterns, but its accuracy decreased if the number of patterns increased. In conclusion, the artificial neural network is a theory that is still under development. Its true potential has not been reached yet. Although the researchers have developed powerful learning algorithms of great practical value, the performances and procedures that the brain uses are still unknown. But sooner or later, the learning of computational studies using artificial neural networks will eventually converge with methods discovered by evolution. When that happens, many empirical data concerning brain will suddenly begin to make sense, and many unknown applications of neural networks will become possible. Thanks for watching.